Hello calculus students, here are with limits of trig functions. We're going to turn limits of some trig functions. First of all, if we look at our 6 trig functions, we can see the limit is just done by a substitution technique. Limit as x goes to c of the sine of x equals the sine of c. But this is only true if the number is in the domain of the given trig function. So if we took a limit as x goes to 0 of the tan of x, that's just the tan of 0, which is 0. But what happens if we go to pi over 2 where the tangent's undefined? We'll have to look at a picture on that later. For right now, here's some typical ones. Limit as x goes to 0 of the sine of 0. The sine of x is just the sine of 0, so that's 0. And if we have a product of 2, we can just distribute the limit over the product. Now, what if we involve other trig functions like this limit? X goes to 0 of the tan x over sine x. We might have to do some trig identities first. Like the limit as x goes to 0, tangent is sine x over cosine x, and now you're dividing by sine of x. So it's the limit as x goes to 0 of, and notice, if I put the 0 in right away and did tan 0 over sine of 0, that would be 0 over 0, which is indeterminate. Kind of like what we did before when we first started doing the definition of the derivative. That means keep looking. Keep looking. And that's what I start off doing here. So by simplifying here, this is the sine x over cosine x times 1 over sine x. So you can see the sine x is canceling. So we get the limit as x goes to 0 of 1 over cosine x. Now we can sub in 1 over cosine of 0, 1 over 1. The answer is 1. Now sometimes you get a limit that doesn't exist, like the limit as x goes to 0 of the sine of 1 over 0. Because as x goes to 0, 1 over x approaches infinity. And what's the sine of infinity? In fact, we can see it as we zoom in on this, that it's just bouncing back and forth between 1 and negative 1. And so you can't really see there's a limit there. Now, testing for continuity. Describe the intervals for which each of the functions is continuous. For f of x equals tan x, we've got those discontinuities there at pi over 2 every time. We've got vertical asymptotes. In fact, we'd have to do directional limits on this. The limit doesn't exist at pi over 2. But what we can do is we can look at the limit as x goes to pi over 2 from the right of the tan of x. And if we approach pi over 2 from the right, then you're heading down to negative infinity. The limit as x approaches pi over 2 from the left of tan of x. Now as we come up this way, as we get closer to pi over 2 from the left, the y values are heading up to positive infinity. So the limit as x goes to pi over 2 of tan x just plain old does not exist. The directional limits don't agree. We don't have a limit there. Now for this other one, x of the sine of 1 over x. We looked at sine before, but in this case, if we look at things, we look at the squeeze function, see that we can always fit this between the function's absolute value of x and negative absolute value of x, and it keeps bouncing in between these two. So as we go to 0, it does have a limit. It's not defined at 0 because you have division by 0, sine of 1 over 0. But at least we can talk about it being continuous everywhere but 0. Wait a second though. Oh, right, because they define this in pieces. At 0 itself, you don't use this function, use this. So that's how they got continuous over the entire real number line. Now here's some special trig limits. The limit as x goes to 0 of sine x over x, and the limit as x goes to 0 of 1 minus cosine x over x. If you just try and look at this by substitution, by subbing in, you get the limit as x goes to 0, this first one, of sine of 0 over 0, which is 0 over 0, which is indeterminate. But we're going to use a little proof here to see why it is 1. And I think a visual proof really helps on this one. Here's a GeoGebra graph where I've put on the three graphs here. Sine x in fuchsia here, y equals x in cyan, and then sine x over x. Now right at 0 it is undefined, but clearly you can see that the limit is getting closer to 1. And that's because basically the sine and y equals x functions start acting more and more like each other, and these values get closer and closer together. So even though right at 0 you have 0, 0, 0, which is undefined, all these points leading up to it get closer and closer to being basically the same y coordinate. And so when I take their ratio here, you get 1. Now the book does a nice job of a formal proof on this, which involves the squeeze theorem. And this is the circular sector idea, that you're going to see that basically this triangle and this green triangle in here, like this, will bound this sector. This sector has to be in between the areas of those two triangles. There's the area of the triangle, tan theta over 2. There's the area of the sector, theta over 2, because it's basically 1/2 r squared theta. And here's the area of the triangle, sine theta over 2. Okay? And you can get these in between each other. And then basically with some tricks with the squeeze theorem, you can, here's your sine theta over theta. Cosine theta is approaching 1 as theta goes to 0. And this is at 1. So that's why the whole thing approaches 1. Now I'm not going to hold you responsible for this formal proof, but I do want you to know these two theorems. And in fact, once you know this one theorem, sine x over x equals 1, you can do this one by just the following little proof. If you take the limit as x goes to 0 of 1 minus cosine x over x, you can figure this out by multiplying by 1 plus cosine x over 1 plus cosine x. So you get 1 minus cosine squared x over x times 1 plus cosine x. Still the limit as x goes to 0. 1 minus cosine squared is sine squared x. And then we can split this up in the limit as x goes to 0 of the sine of x all over x times the limit as x goes to 0 of the sine of x all over 1 plus cosine x. This we just showed is equal to 1. This will be sine of 0 over 1 plus cosine of 0, which is 0. And 1 times 0 is 0. Okay, so just know these two limits and apply them, and we'll practice applying them now. Again, you're not responsible for the proof. I just want to see how our work with the squeeze theorem ties into the proof. Here's a trig limit now. Limit as x goes to 0 of tan x over x. If we just try and sub in and say tan 0 over 0, you get 0 over 0. Whenever you get 0, 0, that's indeterminate, means you have not determined the answer. You have to go back and try and do some tricks to get at the answer. So let's think of tangent as sine x over x, cosine x, and divide the whole thing by x. So it's the limit as x goes to 0 of the sine of x over cosine of x times 1 over x. And rearrange it a little bit here. Limit as x goes to 0 of sine of x over x times the limit as x goes to 0 of 1 over cosine x. This is our new limit definition, our tricky sine limit. Limit as x goes to 0 of sine x over x is 1. This one is 1 over cosine 0. So that's 1 times 1 over cosine 0 is 1, so you get 1. Here's another one, a limit involving a trig function. Limit as x goes to 0 of sine 2x over x. Well, what we can do is write this as the limit as x goes to 0 of the sine of 2x over 2x. Put a 2 up here. Now here's my thinking behind this. I split this up now as the limit as x goes to 0 of 2 times the limit as x goes to 0 of the sine of 2x over 2x. Now this whole thing will just be 2, because 2 is basically a constant function. It doesn't change when x changes. But here we can reinterpret this and say, consider as x goes to 0, then 2x will also go to 0. So we can look at this as the limit as 2x goes to 0 of the sine of 2x over 2x. This is allowed. And now all this, we can think of this as a u substitution. If you let u equal 2x, now you have the limit as u goes to 0 of the sine of u over u, which is the same limit as you used over here. And that's equal to 1. So we get 2 times 1 or 2. Now, here's a little trick you can do with your calculator too. I'll show that to you. That you can go to the calc menu on your calculator. And that's F3. This is the TI-89 now. On F3, you have the third thing down says limit. Limit parentheses. So here's how you do the limit on the home screen then. Limit parentheses, now put in the function, in this case sine of 2x. Oops, you don't know what happened there. I think it's something else. Okay. Sine quantity 2x, comma, as x, 2x divided by x, comma, x going to 0. And let's see what the calculator says. Sine 2x divided by x as x goes to 0. And it says 2. Check, please. Now, I'm not going to accept that as all your work. You can maybe get a point on a 5-point problem for that, but it is a good, nice way to check your work. Okay, flange out.